I welcome all of you, those who are present and those who are in internet connected to this streaming. It's a pleasure for us to start this fourth edition of the PRISM Prize, which is the prize of Istituto Struttura della Materia of the CNR. So today I would like to start and then just to introduce the CNR, and then I start a short presentation about the CNR, and then I will introduce also the prize and the PRISM prize. Okay. So now we are in this Marconi room, which is the one of the room of Consiglio Nazionale di Ricerche, which is the largest research organization, public research organization of Italy. So the number of employees of CNR is around 8,000, 9,000 nowadays. And then we are spread as CNR all over Italy. So we have many sites. There are 18 research areas with, you see the numbers here. There are 88 institutes and then 7 departments. And I will discuss a bit on about the 7 departments. So we cover all Italy, and then this is very important because the research of CNR is really also involve local activity and support the science and the technology also at the local regional level, beside the activity in Italy and at the international level. So we have 7 departments. We are 7 departments, and as you can see, the research activity of CNR is spread all over the science and technology, from biology, social science, the chemical science will be main topic today, and engineering, ICT and technology for energy and transport, biomedical science, earth science, system science and environmental technologies, and physical science and technology of matter. So our institute is in this the last department, which is physical science and technology of matter. And I'd like just to take a few minutes of your time just to introduce our institute before discussing the concept of the PRISM Prize. So this is our institute, so very historical pictures, also you see the colors. The main site is, the headquarters is in, let's say 15 kilometers from here, in the southeast part. The other research area is in the north of Rome, and then we are 2 other research areas which are a bit far from here. So one is in the south, Potenza, research area of Potenza, and the other one is in Trieste, where we have the synchrotron. So it's one of the institutes serving and supporting the synchrotron of Italy activity. We have 60 researchers, 23 technicians, 15 administration people, and beside PhD, postdoc and associated people. So the main mission of the institute is to support and to develop science of matter, having in mind that, this development should be done in a sustainable way. So sustainability is one of the words that is a common denominator that is inspiring our research. Of course, we do science, blue sky science, but also we move also to higher TRL, and then to develop also technology of materials. This is just in a slide, very summarized the research activity, and then we use structural matter, and then we conjugate research structural matter in several disciplines. So we support very much the blue sky research, but then also the applied research, like in biohealth, cultural heritage, ICT, energy and automotive and aerospace. And then today we have many researchers involved in the several sectors. So the institute is very well represented in all these science and technology development. In the last 5 years, we also set up a common platform, which is called PRISM. So this is a catalog and where you can access more than 130 techniques, which are available in the institute. So the institute is also providing all this research capability with instruments, but also with people that know how to do science with this research facility. I just pick one of this research facility among the 130, and this is the synchrotron facility. So as institute, we are running 3 lines of the synchrotron in Trieste, and actually the institute was supporting the development of the synchrotron itself, developing a lot of lines and supporting the ring as well. And we have UV photoemission line, gas phase line, and circular polarization line. And this is what was Elettra. But now we are shutting down Elettra, and we are moving on to Elettra 2.0. It's the new Elettra. You see also the colors. Now we have colors. and we just merged to gas phase and circular polarization. We are developing the MOST line, which is molecular science and technology for dynamic spectroscopy, reactivity, and chirality of low density matter. And the other is BL2, low dimensional laboratory, which is dedicated to spectroscopy of low dimensional system at the surface and interface with high temporal and spatial resolution. So this is a big effort. Several million are spending now on these 2 lines to revamp the synchrotron and to move in Elettra 2.0. So you need to wait a couple of years, 2-3 years, to see and to access this new facility of ISM. Okay, so now we can move to the prize. Okay, so I'm really happy, today to celebrate with you this award. You see, what is the main idea behind this award? So we established this award a few years ago in 2021. And then the idea is to have to provide this prize to scientists that have developed some breakthroughs in the last few years, and let's say 5 years, in the last 5 years. So it's not a career prize. Okay, it's something that is given to active scientists that they are doing innovation, they are doing breakthrough development right now. So you can really discuss with scientists that are changing science and they view our science nowadays. For this is kind of different with respect to other prizes that give prize to the careers, what you have done in all your life. So we are providing the award to those who are doing now the breakthrough. And 5 years is not a large amount of time, so the breakthrough should be very clear, should be very well defined, and then all the world could appreciate this kind of breakthrough development. So we provide this award to activity both in fundamental and research applied, and applied research related to the structure or science of matter. As you have seen, we divide the award in two levels. So there is a senior PRISM award, which is tended to those who are aged over 35, and PRISM Junior, which is tended for those less or equal to 35. How does it work? Okay. So we have a call for nomination. So we ask the international community, we send requests to departments, community networks, and then to nominate researchers that has been distinguished themselves for their breakthrough achievement in the last 5 years. And these stay out 3-4 months. Then there is an international jury. The international jury is composed by those who have won the PRISM Award. So those who will get the PRISM Award have this little duty next year. And then also from the coordinator of the sites, ISM site that I was showing you before. And then the award, what is the award? There's no money involved in the award. But the very interesting point is to celebrate this award together with you today. But also we offer collaboration with between you, with the winner and the institute. So we are trying to foster this collaboration through this prize. This is also, as I said, I mean, it's a very running, dynamic activity, okay, of the prize. Since, of course, you are, very engaged in the research nowadays. Okay, just I remind you who was the winner so far. The first prize in 2021 was awarded by Valeria Nicolosi from Trinity College of Dublin and Matteo Mitrano from Harvard University. In 2022, the winner was Riccardo Comin from Massachusetts Institute of Technology and Stefania Kakovic from CNR-ISM in France. In 2023, the junior category was Nicola Gasperini from Imperial College in London and Federico Capasso from Harvard University. Okay, so far we're international scientists, but still Italian. This year we changed a bit, okay? So the international jury and the only nomination were giving the prize to other people, not Italian people. So it's really a pleasure for me to award this PRISM Prize for the outstanding breakthroughs achieved in the last years in the field of science of matter to two very important, very scientists that are really changing our view of science. So the first is in the new junior category, Professor Nikita Kavokine from École Polytechnique fédérale di Lausanne. Congratulations. Congratulations. And the senior prize is given Professor Alán Aspuru-Guzik from University of Toronto. Thank you. And of course, I mean, now they have, beside the prize, they have a duty, a little duty, which is really very important for all of us. I mean, so we are really happy to have inspiring. So to inspire, we need to be inspired by scientists that are contributing to the edge, to the state-of-art science. So the first talk will be given by Nikita Kavokine from EPFL, and the topic will be the mystery of nanoscale flow, so the quantum plumbing, the mystery of nanoscale flow. And the second talk will be given by Alán Aspuru-Guzik, the material of the future today. So in perfect time. So we invite now Nikita Kavokine to give his award lecture. Thank you. So Nikita, you can use this one or this one as you prefer. What do you prefer? This one, okay? Or this one?
I'll try this one.
Okay. So, okay, this one. Okay.
Hello, can you hear me?
Not yet. Let me see.
I can also speak loudly.
Okay. Okay. Now it works.
Okay, now? Well, maybe too much. So thank you very much, Aldo, for the introduction and the award. And it's really an honor to be here, especially alongside Alán, from whom you will hear next. And actually, it's a real pleasure to be back in Rome after a number of years. In fact, when I was between the ages of 2 and 4, my parents worked at the Tor Vergata campus. And I didn't want to go to daycare as a kid, so they took me with them to work. And there was also no canteen, so but there was a kitchen, and people took turns cooking pasta for everyone. And my favorite days were when we were in charge, so I would watch over the process and then run around the offices and yell, "La pasta è pronta, la pasta è pronta." So some fond memories of Rome, and I'm really glad to be back here and to tell you a bit about my research, which is in the field of nanofluidics. So this world of liquids flowing through tiny channels of a few molecular sizes across. And what I would like to show you is that it's really a fascinating world where the continuum of fluid dynamics meets the atomic and even the quantum nature of matter. Now, we understand very well how liquids flow through macroscopic channels, like a garden hose, since the work of Navier and Stokes in the 19th century. But in comparison, I would say that nanoscale channels are essentially a blank page where we don't even really understand the basic laws of physics. And so, is it really that the Navier-Stokes equation doesn't hold anymore, the fundamental equation of hydrodynamics? Well, the Navier-Stokes equation is remarkably universal. It holds across a very vast range of scales, from oceans to rivers to blood vessels to swimming bacteria, you name it, and even actually down to channels of about 1 nanometer in diameter. So concretely, this means that you can still define a viscosity at about a 1 nanometer scale. However, of course, there is a catch, and as Pauli famously said, God made the bulk, the surface was invented by the devil. And surfaces matter hugely at the nanoscale simply because of a question of surface to volume ratio. So if you look at a 3 centimeter radius garden hose, only 1 in 100 million water molecules in there touch the actual hose. Now, in a 3 nanometer radius nanotube, 1 in 5 water molecules touch the nanotube surface. And so this will make the Navier-Stokes equation much more sensitive to its boundary conditions. So this is really a breakdown of the hydrodynamic universality. Instead of being determined by a single viscosity parameter, the flow is going to depend on all the microscopic details that go into determining these boundary conditions. So concretely, at the macroscopic scale, what you typically do is that you impose a no-slip boundary condition. The flow velocity vanishes at the wall, regardless of what this wall is made of. And so this results in the familiar Poiseuille's law for the fluid flow within a channel, so this parabolic kind of velocity profile, and also Ohm's law for the transport of ions within a liquid. Now, when you go to the nanoscale, people realize that, well, we need some more microscopic parameters to describe the solid-liquid interface, and these are typically the surface charge and the so-called hydrodynamic slip length, about which there will be a lot more in the following. And this already gives you a very rich physics of coupled ion fluid transport phenomena that you typically pack into this kind of transport matrix. So you may have heard of electroosmosis or streaming currents, etc. Now, these surface charge and slip length, they are microscopic, but still coarse-grained parameters. And what I would like to show you is that sometimes this is actually not enough, and we really need to consider the solid-liquid interface at the truly microscopic level of its electronic properties. And this gives rise to a whole new range of phenomena that I like to call quantum interfacial effects that are really beyond the reach of conventional fluid dynamics. And in a sense, this is the ultimate breakdown of universality, because this universality of fluid dynamics, the single viscosity parameter, is replaced by the whole complexity of condensed matter physics. Now, we first came about these quantum effects when trying to understand how water flows through carbon nanotubes. So carbon nanotubes are, in a sense, the Drosophila of nanofluidics, this very well-defined system that is well-suited to figuring out the basic physics. And there was a lot of excitement about 20 years ago over reports that these physics are, in fact, unusual. It was reported that water flows through carbon nanotubes thousands of times faster than predicted by conventional hydrodynamics. What I mean here by conventional hydrodynamics is the no-slip boundary condition. So as I mentioned, typically we assume that the flow velocity vanishes at the solid wall. Now this, however, is an approximation. This is not exactly true at the nanoscale. And what you actually have is a finite slip velocity here at the wall. And so if you extrapolate this velocity profile into the wall, you can define this slip length B here. And so microscopically, the slip length is inversely proportional to the solid-liquid friction coefficient. So the observation here really was that water experiences nearly frictionless flow inside carbon nanotubes. And what is this friction? Well, the common picture of hydrodynamic friction that was accepted thus far was that it's simply a question of the solid surface roughness. Really, the molecules bump into roughness on the solid surface. So somehow the inner surfaces of these tubes were extremely smooth. Now, there were a number of subsequent investigations of water flows through carbon nanotube membranes, but they did not really clear up what was going on. So this is a plot of this enhancement over conventional hydrodynamics versus tube diameter in log-log scale. So you see below 10 nanometers in tube diameter, there's a 4 order of magnitude spread in the reported results for this flow enhancement. And this highlights the difficulty of these membrane-based experiments where you look at several thousands actually of tubes at once. And we only have a clearer experimental picture for larger multi-wall like so tubes where single tube, individual tube measurements were possible. And the observation there is that the slip length actually increases with decreasing tube radius. So in terms of friction, what does this mean? It means that actually water does experience some friction inside these larger tubes, but this friction, oh, you cannot see the points. Well, it goes like this. You have some friction in the larger tubes, but it vanishes as the tube radius gets smaller. So this was extremely puzzling because all these tubes, they have exactly the same inner surface. And this actually has to be also put into the context of other puzzling observations on the water-carbon interface, which is that it was found that monolayer graphene is much more slippery for water than multi-layer graphite. So altogether, graphene, graphite, and these carbon nanotubes, they have exactly the same structurally the same surface, and yet they exhibit different hydrodynamic friction, which you would also have seen in this plot. Somehow you cannot see the data points. They are here in the middle. So anyway, this was really a puzzle and a failure of the classical friction theory. So this is something I tried to understand towards the end of my PhD with Lédéric and Marie-Laure Bocquet. And very quickly we realized that well, we had to start thinking differently about these carbon surfaces, which, well, may be the same at the classical level of hydrodynamics, but they are very different at the quantum level of condensed matter physics. The carbon atoms may be the same, but the electron clouds surrounding them, of course, may behave in a very different way. But there was really a theoretical missing link there. How do we know whether the dynamics of these electron clouds can in some way affect the flow of water on top of them? And so to solve this, we needed to really develop a new quantum level theoretical approach to the solid-liquid interface. And just very briefly, the way this goes is that we formally quantize the water charge density as a free field, a Gaussian field, which is much like a phonon field. So then from the point of view of the electrons, we get something like an electron-phonon problem, which is like a well-known condensed matter problem, except that here it's a non-equilibrium one because we have a water flow. And so we need to use the so-called Keldysh formalism of perturbation theory to solve the non-equilibrium problem. Now, this may seem very formal, but we can push the computations to closed-form results. And what we obtain is that, well, indeed, the solid-liquid friction force splits into two terms. We have this classical term due to surface roughness, which we already knew about. And then we have this extra term that we call the quantum term, and which is really due to the dynamics of the electron cloud. So here you have its analytical expression, and I won't go into all the details, but the important part is that it involves these quantities G here, one for the solid and one for the liquid. So G is called the surface response function, and it's a surface analog of the dielectric function. So really what this tells you is that quantum friction is due to the coupling of charge fluctuations between the liquid and the solid. It's a dynamic analog of the van der Waals force. And in fact, for solids separated by a vacuum gap, this type of effect has been predicted under the names of van der Waals friction or Casimir friction. So what type of charge fluctuations are we talking about here? Well, for the electrons, well, we need to have some free conduction electrons that can move around. And the most important type of excitation is going to be this collective Plasmon mode, a sort of charge density wave, which is artistically represented here. For the liquids, say water in our case, well, we're talking about what you see going on in this movie, these molecular scale charge fluctuations that I generically call hydrons by analogy with phonons, and there are several kinds called the Debye mode, the libration mode, etc. And the way this coupling works is that the relevant hydrons are at fairly low frequencies around the terahertz, and so the lower the Plasmon frequencies in the solid, the stronger the coupling, the stronger the quantum friction. And quite interestingly for us, well, graphene, graphite, well, first of all, graphene and graphite have very different Plasmon modes, and this can be just seen as a question of geometry. In a single graphene layer, the electrons can only move collectively parallel to the graphene layer, and this motion is quite fast at around 50 terahertz frequency. Now, in graphite, the electrons can move now perpendicularly to the carbon layers, and this is much slower at around 5 terahertz. So actually the coupling of the water hydron mode with graphene is weak, so low quantum friction, and with graphite is much stronger, so strong quantum friction. In this way, we understand how graphite can exhibit stronger friction with water than graphene. And actually the multi-wall carbon nanotubes, they essentially interpolate between the properties of graphene and graphite because the layers are better aligned in the larger tubes than in the smaller tubes. And this misalignment effect is something that we can incorporate into the theory, which then provides a good description of this experimental data that you now see in this plot for the slip length of water in the multi-wall carbon nanotubes. So altogether with this quantum friction idea, we understand how graphene, graphite, and nanotubes can exhibit different hydrodynamic friction. They may have structurally the same surface, but they have very different electronic excitations. So this was initially purely analytical theory, but since then we've had various confirmations, both from simulations and experiment, that indeed quantum friction works the way we expect it to. So simulations is actually a tricky point because quantum friction is an effect beyond the Born-Oppenheimer approximation, and so state-of-the-art ab initio molecular dynamics cannot capture quantum friction. However, what can be done is implement a classical proxy for the quantum electron dynamics, and this is what was done by our colleagues from Cambridge, who implemented what's called the Drude oscillator model. And well, I won't go into the details of what they simulated, but the point is that here the red dots are their simulation results. The dashed line is the quantum friction formula with no fitting parameter. So, well, this tells us nothing about whether we're good at modeling the actual quantum electron dynamics. However, once we're given some electron dynamics, the theory is indeed very good at capturing their coupling to the water fluctuations. Then from the experimental side, together with the colleagues in mine, so Misha Bond's department, we now did some spectroscopic experiments where we could see evidence for the microscopic mechanism of quantum friction. And so we use what is called optical pump terahertz probe spectroscopy. So the idea is that we have a piece of graphene in a liquid flow cell where we can put different liquids. We heat up the electrons in the graphene with an optical pump pulse, and then we watch the electrons cool with a terahertz probe pulse. So effectively what we measure is the cooling rate of those graphene electrons when it is put in contact with different kinds of liquids. And so the observation is that the electrons cool faster in the presence of water or heavy water than in the presence of other liquids or no liquid at all. And this we can really attribute to a direct energy transfer between the graphene electrons and the water, which is really the microscopic mechanism at the root of quantum friction. And the smoking gun here is this isotope effect, the difference between water and heavy water, which is very well reproduced by the theory. So altogether, we realize now that we have to start thinking differently about these nanoscale channels, at least as soon as there are some free conduction electrons within the walls. So they're really not these passive hydrodynamic conduits. They are very dynamical systems with these wiggling electronic clouds that couple in a very specific way to whatever is flowing inside through quantum friction. And so this coupling hosts a lot of potential for new functionalities in nanoscale fluid transport. And really my lab's mission is to do the nanoscale engineering, or quantum plumbing, as I like to call it, to realize this potential. And so in the time I have left, I would like to just give you a flavor of how concretely we're going about it. So the main perspective that we have been recently exploring is the coupling of liquid flows and electric currents. So in fact, quantum friction amounts to a direct transfer of momentum from a flowing liquid to the solid's electrons. Now, the electrons, they cannot relax this momentum infinitely fast. So of course, they accumulate some momentum, which means there is an electric current. So we realized this non-trivial and actually previously unknown fact that when you flow an electrically neutral liquid on top of a conducting solid surface, well, you induce an electric current. We call this hydroelectronic drag because this is in fact similar to the Coulomb drag effect in condensed matter. Now, if you have hydroelectronic drag, it means you must also have the reverse effect, where you drive an electric current through the solid, and this induces a liquid flow. This one we call quantum osmosis, because actually electroosmosis is taken for something else. And well, altogether, you can actually define a full hydroelectronic transport matrix for these coupled fluid electron transport phenomena, if you consider this kind of channel that is coupled both to a hydraulic circuit and an electric circuit. And by now, we have pushed the theory to compute all the coefficients of this transport matrix. So quantum osmosis, in fact, provides a very interesting nanoscale pumping mechanism because as opposed to any other kind of pump, it doesn't really push the liquid. It actually pulls on its charge fluctuations. And this is something we're experimentally actively exploring. But what I would like to focus on in the following is hydroelectronic drag. This one is very interesting because it provides, in a way, regenerative braking principle for fluids. So it converts hydrodynamic friction, which is usually associated with energy loss, into a useful electric current. And so we may ask, what is the efficiency of this energy conversion? So by efficiency here, we mean the ratio of electric power we get in the external circuit to the hydraulic power we apply to pump water through this nanotube. And what we find is that the efficiency is controlled by a dimensionless figure of merit called Z, which has a somewhat cumbersome expression, but the point is that it compares the rate of momentum transfer from the liquid to the solid, the quantum friction coefficient, to the rate of all momentum loss processes in the system, be it classical friction on the surface roughness, viscous dissipation in the bulk of the channel, electron scattering on defects or phonons. But the point here is that the numerator and denominator in this formula are largely independent. They can be optimized separately. And this is quite different, for instance, from the case of thermoelectricity, if this is something you're familiar with. And so actually you can achieve quite large values of this hydroelectronic figure of merit. For instance, for these multi-wall nanotubes where we predict high quantum friction, we estimate a figure of merit as large as 11, corresponding to a conversion efficiency in excess of 50%. And so in this way, hydroelectronic drag provides a principle for a seemingly impossible nanoscale turbine. So at macroscopic scales, a turbine is extremely efficient for converting hydraulic energy into electric energy. However, turbines do not work at small scales. And for this reason, there are a lot of industrial processes where with flows that are too weak to spin a turbine and are just lost. For instance, this happens in filtration or desalination, as illustrated here. Also things like evaporative cooling, pressure retarded osmosis, to name a few. And so this hydroelectronic drag actually provides a principle for recovering some of these waste flows. So now I have told you about liquid flow inducing an electric current inducing a liquid flow. What happens if we put these two together? Well, then if you have two liquids separated by a solid wall, the flow of the top liquid is going to induce a current in the wall, and this is going to drag the bottom liquid, so effectively the flow tunnels through the wall. We have a flow tunneling phenomenon. So now we have thoroughly investigated this flow tunneling, both through analytical theory and the semi-classical simulations from our colleagues. And I won't go into all the details here, but the point is that the intuition is actually correct, and this kind of flow tunneling can occur through walls on the 10 nanometer thickness scale. And this, I think, is really has far-reaching implications, because this is completely at odds with macroscopic hydrodynamics. So in hydrodynamics, there is no way that two liquids flowing in parallel pipes talk to each other. Here at the nanoscale, we realize that this is indeed possible, and this cannot anymore be captured in any effective boundary condition for the Navier-Stokes equation. So actually, we might need to revise this slide that I showed you at the very beginning, and we might need to reinvent nanoscale hydrodynamics to really treat the degrees of freedom of the liquid and of the surrounding solids on equal footing. And so this is really what I would like to leave you with. I hope to have convinced you that at the nanoscale, liquid and electron flows are really intertwined, and this has a range of both fundamental and practical consequences. If you would like to learn more, there is this recent feature in Physics World magazine, which I think is a great place to start. And now all I have left is to thank my group at EPFL, the amazing quantum plumbers who have been following me in all these pursuits, my collaborators around the world, and most importantly, thank you all very much for your attention.
Some ideas, so it's really a lot of ideas came to my mind. Please add.
So this is cool. Now that you know basically that you want to have something that has, very, facile plasmons, what is the material that you could engineer to be the best at having flow of liquid over it, beyond graphene, for example? Is there anything? What would be the ultimate material?
Yes, so this is a great question, and we're indeed really trying to outline the conditions for materials to exhibit the highest quantum friction. So in a nutshell, what you want is actually slow plasmids.
Slow plasmon, sorry.
Yeah, that stay at low energy at very high momentum, because the higher the momentum of your excitation, the more momentum you can transfer from the liquid. And so you want narrow bands essentially and very large Fermi surfaces. So, well, twisted graphene is a good candidate, for instance, because of the flat bands, but then this is quite impractical to use. Some metallic TMDs could be good candidates because you can dope them to put the Fermi level in the middle of the Brillouin zone. So essentially anything with a large Fermi surface.
Just a question of curiosity, because now we are using a lot of water splitting, okay, for hydrogen production. Do you think that this kind of nanochannel can be used effectively for also to improve splitting of the water?
I think there are some perspectives there, and they are probably not to be found in my work, but rather in the work of colleagues, in particular from Cambridge, who have been looking at the phase diagram of water in strong confinement, particularly 2D confinement. And the one very inspiring thing there is that they're starting to see superionic phases, so phases where water splits spontaneously at much lower pressures than what you would need without confinement. So maybe there is this kind of perspective.
Okay, so I don't see any. Yes, please, Alessandro.
Thank you very much. Indeed, very interesting presentation. I have a question both for applicative but also basic science point of view. So can you envisage any role of ionic species dissolved in the water that you make flow through these tunnels? So what would be the effect of ionic species and their concentration especially? Thank you.
Yeah, I think that's a very interesting question that we also asked ourselves. So we recently looked at indeed how these charge fluctuations of water change when you add salt. And roughly speaking, you have more charge fluctuations. So you add some ion-specific modes and you increase the friction, but not by huge amounts. What is interesting is that you can have a different friction between the water and the ions, and you could envision this difference as a pathway for water-ion separation. So desalination, possibly even ion-specific desalination. Then also on the point of ions, for these energy conversion applications, actually what we like very much is that this mechanism here does not require ions. So when you try to scale up anything like that, the first problem you encounter is the electrodes. You generate some ionic current and then you need to convert it into an electric current. And here you really don't need electrodes. You have a purely physical mechanism that transfers energy from the liquid to the solid.
Okay, so thanks a lot, Nikita. So now let's move to the second hour talk, which is given by Alán Aspuru-Guzik. Please, Alán. This is the tool, and this is also you.
Thank you. Aldo, thank you. It's an honor to be here. I just realized something cool. This is the Institute of Structure of Matter. When I was undergraduate in Mexico, I wanted to study biochemistry. But when you start chemistry in Mexico, there's actually 4 courses that you have to take. Calculus, what was it? Another math course, algebra probably, calculus, algebra, and then you have to take general chemistry, and then structure of matter. So they changed our courses in Mexico when you take a course called Structure of Matter that tells you the beginning of quantum mechanics. I was so fascinated by that course, then I changed my course from biochemistry to quantum. So it's an honor to be here in the Institute of Structure of Matter, actually, and receiving the award of Structure of Matter. So really special. So today I'll be telling you about our work trying to accelerate materials discovery. Okay? Let me see the clock. So even since the very beginning of quantum chemistry, Perlov-Levdin said that we are here to calculate properties of matter. Like, for example, Nikita was telling us about how to potentially extract energy out of flow, right? To actually do something useful for humankind, right? So that's an example of what we are here. I'm really thinking about translational research, trying to do some fundamental research, but also trying to advance technology to make things happen, right? So we have that responsibility, especially in this century that is so chaotic. So with Marcus Reicher and Roland Lind back in 2017, okay, and then published in 2018, it almost feels ages ago. We wrote this paper that was thinking about what is the future of computational and theoretical chemistry, right? What are the things that we should do in this century? And we argue that, okay, you know, like we have to think about different areas of theory. So I'm going to tell you a little bit about them. So what is the 20th century physics? I think the 20th century physical chemistry, you can define by this slide by Samuel F. Boyce, which basically I think should have gotten the Nobel Prize instead of John Pople. Actually, he was the first one to do, in 1955, a general quantum chemistry calculation on a classical computer. Okay, and his students and colleagues wrote this about him. He came to the 1955 Boulder, Colorado conference with a printout of a first general quantum chemistry package. In one side entered a chemical question, in the other side came out a chemical answer. Now, if you read it from the old perspective, right, reading it like old-fashioned, that means XYZ file energy or XYZ file molecular dynamics, right? Forward simulation. But in the 21st century, you can really use a question in Italian and get an answer in Italian with the current technology, right? So really, you have to reread this phrase, I think, and think about what is our role. Our role is to answer questions with computers, right? So that's what we have to do in this century. So I would like to say that in the 20th century, this is what theoreticians and computational chemists did. And we, of course, still do that today. So if you're one of those people that run DFT, no problem. You can still keep running DFT, okay? But there's other things we can do nowadays that are interesting as well, okay? So I'm trying to say there's more stuff to do in the 21st century. And I argue here that we need to think about human-computer interaction, think of artificial intelligence, robotics, virtual reality, all the technological drivers of this century, right? Those are the drivers that are going to allow us to actually advance theory much faster. And that's what my research group does, okay? Even though it's still called the Matter Lab. So at the end of this talk, I'll tell you about this vision, right? So in 2017, we imagined this dialogue between an organic chemist called Jane and a robot chemist called Organa, okay? So Jane was asking Organa, can you please make me these organic light emitting diodes? So I'm very interested in designing these materials. And Organa said, yeah, no problem, just order these materials. They will come, then I will make the reaction, I'll make the measurements, and I'll come back to you and I'll tell you what happened. Right? So that was that vision was the beginning of this idea of the self-driving lab, the modern version of the self-driving lab, as I'll tell you, and how we started working on that. So anyway, that's a cool paper, but let's start talking about self-driving labs. I mean, that's interesting. It's an analogy to the self-driving car, right? Some sort of closed-loop system that makes decisions on the fly based on what happens, right? The same way a say, Tesla car is deciding where to go. Basically, the same thing can happen with a self-driving car lab. So why are we trying to do self-driving labs? Because the design of molecules and materials is extremely slow. Quantum dots for light emission, solar cells, batteries, you name it. Every material that you're going to think about, even the laser, takes about 20 to 30 years from fundamental discovery to commercialization. So by the time there is some quantum pump that Nikita just discovered, it will be 30 years from now, unless he uses robots and AI to actually accelerate his materials discovery. Otherwise, you will get the senior prize, when the first time this happens, right? So we're trying to lower it down by a factor of 10, and a factor of 10 is not that much. If you can discover a material in 1 year and with $1 million, we can change the economics of discovering of materials. Investors will be much more interested, and we could become relevant to society, right? Because if you guys are saying, oh, we're going to solve climate change today at this speed, that's not true. You discover a material today, the world is going to be done by the time your material is commercialized. So we need to accelerate how we discover materials and molecules. So, okay, so you might say, well, Alán, but high-fructose experimentation has been there for a while, HTE. Yeah, HTE is fine. Of course, we have the robots to do many materials at once for a long time. The problem is we didn't know what to make. If you just make a material in a grid, right, basically with an Excel, you're shooting bullets in the dark. Okay, basically, it's very stupid to actually search materials in linear fashion. Okay, so you want to think about better ways to do it, and I think turns out AI gives you a very, very experimental data point efficient way of doing it. Okay, Bayesian statistics allows you to say, based on my prior, what is the next best experiment to make? Okay. I pioneered also generative models for chemistry. Generative models are very important. I don't have time to tell you about generative models today, except that, of course, they generate molecules for you. Say, this will be a great molecule to do this or that. The problem is that usually it's very hard to make that molecule. So we argue is, let's say you build a robot that makes molecules from materials. You're going to use AI and calculations to explore the space that your robot can make, right? So your robot can make materials depending on what robot it is and what are the source materials. That chemical space of available things you can make is where you can search the best material, right? So that's what self-driving labs likes to do, likes to really optimize on what's practical and possible. Okay, so that's the difference. So, well, automation of chemistry, I told you, very old. Like 1966, this is actually Bob Merrifield's automatic synthesis of peptides. Arguably, because the chemists were there, they accelerated biology, right? Because biology is modular, as I'll come back in my talk. So biology, you can make RNA, DNA, sugars, and proteins, all of it with very few reactions in iterative coupling manner, right? So if you can automate those reactions, suddenly you can actually print RNA or print DNA. And that's why there are in the biology labs vending machines where you press a button and you come out with a DNA strand. If you have seen them, they're incredible, right? So Bob Merrifield did the first solid-state synthesizer for peptides in '66 and got the Nobel Prize in 1984, right? They were so important. So automating chemistry is important and has changed biology mostly. Unfortunately, not chemistry. And we'll get back to that. But the first self-driving lab, as I told you, closed-loop control of a particular chemical reaction came out when I was 2 years old. Okay, this is a paper by Winnikov from SK, the now GSK. So the abstract could be an abstract on the journal Digital Discovery, the journal I edit nowadays. If you replace BASIC, how many of you have programming BASIC? Raise your hand if you have programming BASIC. Yeah, only you and I? Nobody else has programming BASIC? Oh, no. Okay, so you can replace BASIC by Python. Raise your hand if you have programming Python. Okay. And then ASCII by smiles or selfies. Okay, basically the same thing. So you see how science has very long cycles, and the idea of the self-driving lab is actually quite old. Okay, but we wrote this perspective saying, okay, what's going on in the self-driving lab? You need to have a lot of control software that controls your robotic experiments. And now you can think about what I think are exciting things for theoretical chemists to do. Maybe we want to work in computer vision. Maybe we want to work in Bayesian optimization. Maybe we want to think about how to store the data, learn from it, and build huge data lakes across the world of all the chemical data, right? Those are the things that I think are interesting to do in theoretical chemistry this century. So we wrote 2 reviews. You can download them in chemical reviews. One about self-driving labs, starting with those very early papers all the way to now. And then in Digital Discovery, which is the journal I edit, we have one that I really like about it. It's about frugal self-driving laboratories, right? With all these funding cuts, I just saw your protest about funding cuts outside here. We have to think about how to make these laboratories actually affordable, especially for the developing world. So really think about how to make very inexpensive self-driving laboratories. And anyway, here are some of the elements. Again, I guess the slide is a little bit repeated, but here are some of the elements of what I think are going to be quite important. And in the University of Toronto, especially with Acceleration Consortium, I'll tell you about, and my group, we really think about pretty much all of these aspects. So there's a lot of robotics. And here in Italy, in Genoa, there's the IIT, where they have very good robotics, and we have imported very good researchers. Like Kouros Darvish, like one of my top right-hand people in robotics, comes from Italy, from this institute in Genoa. So if you're going to collaborate with cool robotics people, go to Genoa. I like those guys. So this is actually an example of a very frugal self-driving lab. This is Andres, former postdoc in my lab. He became a professor in Mexico. And with $200, he built a condensation reaction self-driving lab with $20 pumps. Okay, so this is an example of what you can do, for example, for teaching and even for research, if you are actually frugal about making self-driving laboratories, right? So this is, of course, a very basic one, but what can you do with $300, right? So, but on the other side of the spectrum, we just got the largest grant ever given in Canada, 200 million Canadian dollars, which is $150 million. I don't know how many euros is that, but it's a lot of money basically to drive self-driving laboratories. So If anybody wants to come visit and see what we're doing there, we're building self-driving labs all the way from inorganic chemistry, all the way down to organ on a chip, polymers, organic synthesis, drug discovery, etc. We're going to even have a new building there, basically, that's going to house them by 2026. So I'm going to tell you a story for the remaining of my time of a self-driving lab, the first one I built, actually. So it took me the longest, it cost me the most, and it was the most complicated. Now, of course, we can make self-driving labs. The record is about 2 or 3 months. I had a student come from Spain to my lab. By the time I got to meet with the student, he had built a self-driving lab. Okay, I was so busy. So I meet with the student, he says, I just finished my self-driving lab. It's actually doing these measurements. I was like, wow. Because there's a learning curve, right? The more self-driving labs you build, the easier, the simpler you make them, the more equipment you have, the more you know how to do them. So if you guys start building self-driving labs in Italy, and I know actually Antonio is building one here. Anybody else is building self-driving labs? Well, Antonio is our pioneer here, Il Pionero. So it's going to be very cool to see how you build self-driving labs here. But the more you build in Italy, the cheaper and the simpler you're going to learn how to build them. Okay. So this is my first one, so it's going to be very big and busy and clunky. Okay. But it starts with a story. How many of you have heard of Henrik Schön? Okay, you. Okay, only one of you. Okay. Well, luckily he's not Italian, he's German. Okay. And or Austrian. I think he's Austrian, actually. And he was the biggest fraudster, at least of around when I was a graduate student. Okay, this guy was in Lawrence Berkeley lab, but he was also later in Bell Labs. Actually, he was in Bell Labs. And he basically was faking organic semiconductors, organic superconductors, a big fake. I mean, Federico Capasso was his boss, and Federico Capasso didn't discover the fraud, okay? Okay, Capasso was the boss of Bell Labs, I think, at the time. And you know, this guy was under Capasso, and Capasso was like, oh, great results, right? Obviously, he was faking the results so well. But there was one postdoc that caught him. You can see here that Stephen Forrest questioned the results. Do you think it was Stephen Forrest or his postdoc, the one that discovered that this was fake? Probably his postdoc, right? His postdoc is Chihaya Adachi, okay? My slide is wrong. I'm going to skip that. His postdoc was Chihaya Adachi, okay? This guy here just visited Toronto actually 2 weeks ago. Chihaya persevered. He's Japanese stoic. He works for years. And about a few decades later, in 2017, he was able to show the first solid-state emitting organic lasers that actually have very good efficiency. Of course, this will be able to replace the screens in your cell phones and in augmented reality displays because of this beautiful super ultra narrow emission. You can see the laser emission versus a molecular emission, right? So imagine you have electrically controlled now emission in your device. So it's the next generation. It will actually make your augmented reality glasses transparent, and of course, super cool technology. The reason we picked it for self-driving labs is because Chihaya had only published about 10 molecules by the time we started in 2017. So we wanted to start in a material class that nobody had actually pushed before. Right, so I'm a physical chemist, so I want to minimize absorption and emission, or the overlap between absorption and emission. Otherwise, the substrate self-absorbs, and that's not good for a laser. Okay, minimize excited state lifetime and minimize intersystem crossing. Okay, so you have to do these physical chemistry optimizations to basically make a molecule look like an atom with a huge oscillator strength. Okay, so we got this DARPA grant called Madness. These are the 4 characters that collaborated with me. If you guys know some of them, it's appropriately named Madness. Okay, so Marty, Lee, Bartosz, and Jason and I had different superpowers to this, right? This was kind of like the Avengers. We got together to try to solve this problem. Okay, so we cannot make with robots the self-driving the devices yet. I know Antonio will do. Antonio will do the full, characterization all the way of the devices. But we, unfortunately, can only make proxy measurements in solution, okay? Then we purify the compound, send it to Japan, and Chihaya Adachi makes the devices, right? But that's changing. We're going to work with Chihaya to make an automated device-making architecture. So how do we do it? We inspire ourselves in biology. This is where the superpower of Marty Burke comes in. Marty's career has been pioneering the idea of modular organic chemistry. Why can't we make molecules the same way the biology makes molecules? Organic chemists, raise your hand if you're an organic chemist. Organic chemists have about 10,000 reactions that they usually use. There's about 100,000 published, but they use about 10,000. Okay? Arguably, you could imagine reducing that to the principal components of reaction chemistry, use very simple reactions and automate them, right? And one example of them is carbon-carbon couplings, for example. So that's what Marty Burke has been working on. So that's what we think about. We think about how to increase the yield of organic reactions, how to make them more robust, and in principle, make more complicated libraries of chemicals that are useful for materials rather than drug discovery. So this is a self-driving lab. It's called Madness because I'm a theoretical chemist running an organic chemistry, analytical chemistry, and physical chemistry labs in the same place, right? So you can see here the synthesizer, you can see the HPLC, and you can see here the ultra-fast equipment, right, to measure basically the pump probe. Now we have an excited state absorption setup. And recently we put 2 more stories because my lab is very small. So now we're going to have 3 stories of optics, okay, that we're working on. Combining fluids with optics. And then we can see, for example, the lifetime, or we can see here, as you can see, small absorption and emission. So that's what we're able to do in about 1 weekend. We can now make 40 molecules, okay? So this is an example of the first reaction, a very simple reaction that we did. This is actually Andres and Tony and Kazuhiro Hota and many people in my group. We took basically these cores and we just capped them with this very simple cap, BSBCC cap, okay? So we said, okay, bring it on. Let's actually couple it in a single weekend. The challenge to my group was we want to have a paper that was done in a weekend to show the self-driving lab works. So that's what that was on, okay? So here is the powder dispenser, okay? This is the most expensive balance in the world probably or something, but it's pretty good. So if you want to really automate powder dispensing, this is the one we use. It's a Chronet Quantos, all controlled by our Python. And this is the piece of equipment that I will not buy one again. This is called a ChemSpeed. So it turns out we only made 5% of our molecules on this expensive platform, and we built our own synthesizer for the 95% remaining ones. So if you have one of these, if you want to buy, don't buy this, okay? Just don't buy this. This is just too much and doesn't work. This is the Swiss. Now we can talk about the Swiss, okay? But still interesting piece of equipment. Anyway, here is basically the kind of main single plot I'm showing you here. I'm telling you everything at a very high level. On the y-axis, you can see the optical gain, the probability that a molecule will give you back the photon, right? In a laser, you want to have a hot potato type of situation. The molecule gives you back the photon in the excited state very quickly. Obviously, you put it on a cavity to emit the light faster. But this is just in solution. The stimulated emission in solution, as a function of the wavelength, this was Chihaya's best molecule. And in our first run, we were lucky. We got already several molecules that were better than Chihaya. So back then, that was the record holding in a single weekend. Self-driving lab. We purified one of the molecules, sent it to Japan. You can see here the narrow emission, and you can see here the excitation energy threshold. Now, organic lasers are not practical nowadays. They last about 2 hours because there's a lot of charges that you need to actually accumulate. So there's a lot of technology that has to be done for optimizing the layer structure to make it actually more efficient device. But the same thing happened to OLED. And now you watch OLEDs in your cell phone. So it's just a matter of time, and we can also build robots to automate that process as well. So now, how do we got this to work? We actually developed a project called AC/DC, okay? Basically, we do not have a single self-driving lab to do everything. We need to actually do it across the planet with all the collaborators, okay? So basically, the sun never set in our empire, okay? We have basically a lab in Japan, a lab in Poland, a lab in Toronto, one in Urbana-Champaign, one in Vancouver, okay? So we had to develop software to actually control all of this, and the software is called Organize It. So we basically ship chemicals all around the globe. So I'm a Mexican, so I like to ship white powders all over the planet, okay? And basically, you can see here all the logistics that we had to do, right? So if we had a molecule, and that molecule suddenly rots out in lab A, our database has to know that there's not much molecule in lab A, so that the AI does not suggest that reaction there. Our database needs to know when a reagent arrives, so that the experiment the next day happens in a different part of the world. Also, when equipment is down. As we were building the self-driving labs, obviously they were all down all the time. So it's not that a self-driving lab is going to be working all the time. Sorry, Antonio. Your self-driving lab is not going to work most of the time. When it works, you will publish a paper and it will stop working again, right? Because you're building it, you're doing different things. So it's very, very hard. But we build self-driving labs that look like these. These are basically called a machine. This is the one in Urbana. This is ours. Ours is called Medusa. This is the the machine that I told you is too expensive, this ChemSpeed, you can replace by this synthesizer. And this is the famous ChemPuter by Lee Cronin. We cloned one in Vancouver in Canada. So with all those different molecules, we make either the boronates, TDA, BDA boronates that we used for the reactions, or we also do the coupling of the different molecules, and then we ship everything to Toronto for measurement. So that's how the workflow looked like. We actually make a library of about 190,000 compounds just by actually combining different commercially available compounds. We have to actually change the caps to boropin, so we need to buy the MIDA boronates and then change the caps by hand. So there's a lot of also good organic chemistry involved to actually make the libraries. But once we have them, then we can actually do the Suzuki coupling. Okay? I'm skipping a lot of the synthesis here because I realized I have too many slides. But this is Medusa. This is the platform. We actually already submitted this paper. Hopefully you can see the protocol soon. It cost about $5,000 to build one of these robots. And basically, it's all open source, controllable by Python, very inexpensive hardware. And we have actually used it to do electrochemistry, inline reaction monitoring, and organic synthesis. So if you buy these pumps and control them with Python, you can actually build a versatile number of experiments in chemistry just by changing where the wires go. And therefore, I recommend you to actually build Medusas. They're actually easy and very practical. And this is our Medusa with a camera making these organic lasers in a two-step, one-pot synthesis. This is an accelerated video, but you can see how with those very inexpensive pumps and these very disposable vials, we're actually making the organic laser right there. Right? So that's kind of how you automate chemistry. You know, the student comes in the morning, sets up the reaction, right? And then at the end of the day, you have 40 vials that you can put in your ChemSpeed again to actually measure the properties. So now you might say, well, is this useful? Well, one of the most useful reactions in the world is the Suzuki reaction, the one I've been telling you about. Is it really optimal? Do we really know the optimal conditions for Suzuki? Or are there better reactions that we can make? Right? Like better genetic conditions. Imagine you guys are a bunch of diverse substrates. What is the single set of reaction conditions that will give me the highest possible probability of having a reaction and the highest possible average yield? That's an interesting question for AI. And you know, usually organic chemists just imagine those conditions, try them and try them again. But if you use AI, as we did here with Marty Burke, we set about 40 different substrates that were as diverse as possible. And then we optimized over 4 generations in that diverse substrate using Bayesian optimization, the Suzuki reaction. And just on the side, we got this paper in Science that allowed us to really double the yield of our screening, right? What is nice about this paper is that this paper now allows anybody that does Suzuki to double their yield. If they don't know anything about the substrates, they can try our reaction conditions. They are in average going to be twice as better as the 2009 reaction conditions published in JAX, okay? So that gives you an idea of why AI is going to be so important. People are going to start optimizing the Buchwald hardware reaction, and now the Negishi, and etc. Right? So the 10,000 reactions the organic chemists have not optimized, we can now optimize them and make them doubly efficient, probably. I don't know if doubly efficient, but. So now we were able to actually make in that sprint about 1,000 molecules. Okay, still very expensive per molecule to do what we did. Okay, but we did about 1,000 molecules guided by Bayesian optimization. This is how the racks look like. And we were able to, let me see the time. It's just really don't have too much time left. But anyway, I know when but we were able to actually use, well, let me tell you a lesson. One of the lessons, I'm going to start with this. Sorry. I'm trying to decide what to tell you in a compressed amount of time. One of the lessons that matters is DFT and these kinds of things do not produce usually the property. Forget about that. Okay, I'm a theoretician. It's very, very hard to say, yeah, I'm going to calculate this and it's going to be measured experimentally. Good luck. Okay, you need to actually massage it a lot. And usually people do regressions, as I started doing when I was working in organic solar cells, for example. You have linear regressions, regression process regressions. That's kind of level 1. For an organic laser, it's way harder because in the organic laser, I need to predict the side-state lifetimes. So we have worked in trying to do it by ab initio, having a molecule in water fluctuating and predicting the lifetime. It's actually pretty hard. We have not been able to do that. Maybe some of the theoreticians here can try to do that, but try to predict the excited state lifetime of one of these organic laser molecules. in the solvent, etc. It's going to be very hard. So what we say is the following. Everybody now also can build machine learning models for DFT. If you actually open up almost any paper in any journal, including Digital Discovery, the R squared for any DFT machine learning model with the calculated properties is going to be about 0.9. Okay? So say, I want to predict the gap with a machine learning model about 0.9. I want to predict the dipole. I want to predict whatever. Okay? So we did that. We got those features for these molecules, and then we built a latent space out of that machine learning model, and we Bayesian optimized in that latent space. That's lesson number one. The shaped latent space is what matters for experiment. There's a lot of lessons in this paper. It took us 5 years to learn. The other one that I don't have time to show you the statistics is if you were doing prediction, do not predict absolute value, predict ranking. Okay? If I want to know if a material is better than the other material, I don't need to know by how much. I only need to know, am I better than that one who works? Does that make sense? So if you predict the pairwise ranking between your materials, you can have an R squared, we call it tau omega. The equivalent of R squared is about 0.9 compared to about an R squared of 0.6. So even if you have a crappy model that has an R squared of 0.6, it might have a tau of 0.9. So if you're doing machine learning, try to always predict the ranking, because ranking is going to be easier than absolute values. Does that make sense? So that's the second lesson. If you don't remember anything about this lecture, just remember Alán told me to rank, not regress. And you'll be very happy, okay? So I'm going to skip a lot of the machine learning stuff. Well, maybe this is important. How do you optimize your experiments? I told you that you use the prior information from your data to actually predict the next best experiment to make. That tool is called Bayesian optimization. Now, you can imagine here, you have certain experimental data points. You imagine all the possible functions that pass through them. And then by getting more extra points, you can actually reduce the error or the uncertainty that you have between those data points. Now, you might say, well, I'm going to use a regular tool for Bayesian optimization. We tell you, if you're going to do chemistry or material science, there's a lot of things that we care about. And my group and other groups around the world have been working on chemistry-tailored Bayesian optimizers. For example, we chemists usually like to order our properties. We want to get a molecule that has low cost, high efficiency, is not toxic, etc. Depending on your project, you want to think about those objectives and then Pareto optimize those objectives in series, right? If what is important more to you is yield, then you put yield first. But maybe if to you is, I don't know, photovoltaic efficiency in your robot. So then you're going to put that first, right? So this Chimera algorithm that we have here allows us to actually do that kind of like ranking of the different objectives. So we have a lot of data, a lot of different algorithms, about 9 or 10, that we have published around the years to actually help chemists do Bayesian optimization. And they're all in this code called Atlas. I think they're all named after Roman kind of things here. Actually, I'm changing the convention now. It's going to be Mayan gods and Aztec gods, and you know. Anyway, okay. So now I'm just going to end with the future. Okay. Well, okay. Not this. I guess I really want to end my talk soon. So I want to show you something. What is the result? I missed it. Sorry, guys. I actually hit a slide. I'm a disaster today. Well, no problem. After 1,000 rounds of optimization, and I missed that plot, we're able to find these 3 lasers. These are the best lasers in the world, okay? So now the plot that I wanted to show you is how, as we continue advancing, we get better and better and better materials, almost every round of experimentation, okay? This is a terrible talk today. Okay, so as a theoretician, you might ask yourself, what is the best possible organic laser? That's why I asked this question to Nikita. I like to ask myself the question, so what? What is the best possible thing I can make, right? So in this particular case, we take the formula for stimulated emission cross-section and we say, okay, we really want to have a perfect quantum yield. We want to have the best possible lifetime that we have found in any organic molecule in the world, etc. That will give us like the upper bound of what is going to be possible in the field of organic lasers. And if you do that, you can see here in a log linear plot or in a linear plot, actually how it's going to be about a factor of 10 or so, a little bit more in the blue region, and several decades of potential optimization in the red region for organic materials. So there's a lot of extra, you know how you say that? A lot of extra work that we still have to do in the field of organic lasers. the brightest molecules in the world. Okay. So this woman just resigned from her post yesterday. She was basically the equivalent of Kamala Harris in Canada, the vice president of Canada, the deputy prime minister. She came to my lab. She announced $5 billion more of research funding in Canada, literally between the self-driving labs. And without gloves, she was handling the molecule here. Okay, a little bit of chemical safety problem here, but there she is handling the brightest molecule in the world. Okay, so I was very proud to have her in my lab. Now she's not part of the government anymore, so who knows what's going to happen in Canada. But now, what are we working on, right? So the epilogue is actually mysterious, but we optimize our chemistry. Now that we have a new chemistry, right? Now we had that chemistry of 190,000. We thought, are there better fragments? So Chihaya had published better fragments. We thought about rigidity and other aspects of the organic laser molecule. In our first run, we had top performers again. So we are going, guys. But the identity of these molecules remains secret. And the other thing is that we're focusing a lot in near-IR. You guys remember near-IR had a lot of gain? So our next paper is going to be all about the near-IR lasers. This is how they look like. Aren't they super cool? Anyway, those are the brightest molecules in the world. Okay. I was allowed to spend a little bit more time in my talk. Actually, I was allowed. Okay. So I want to tell you about 10 minutes or so more about the lab of the future. Okay. So what is going to be the future? So the future is not going to be these liquid handlers. The future is going to be arms. The price of robotic arms is lowering exponentially low. How many people here have robotic arms in your lab? 2 of you. How much do people think these arms cost nowadays? An idea. Give me an idea. About $4,000, $3,000. You can buy one. Actually, Han Hao, one of my collaborators on this project, he's such a nerd, he wanted to have it in his house too. So with his own money, he bought an arm and he cooks with it. Okay? Seriously. He's making Chinese food with his arm. Okay? So these arms, this is about $40,000. Okay? It's a Franca arm. But you saw it was taking pictures of the glassware because at the time there was not enough data to actually handle transparent glassware. So why am I telling you this? It's going to be very hard to take any lab around the world and convert it into a high throughput lab. The future is going to be a humanoid robot entering your lab and doing experiments the same way a human is doing them, right? Think about it. It's a graduate student that does not strike, right? Just kidding. Okay, obviously it's not true, but bad joke. But it's basically something that will help us actually do science, right? Having a humanoid robot coming around your lab. So this actually is a computer vision data set that we built called TransparentNet that allows us to actually have, at the time, state-of-the-art transparent object detection. There is a big problem with transparent objects because light can actually be reflected and transmitted at the same time, as you can imagine. So we were able to actually have the best transparent object detection. And you can see here some of the experiments that we did back in 2003. We started with very simple things like solubility experiments. So we had to teach the robot how to do pouring. It's interesting, but there were no publications with pouring skills that we could figure out. Okay? So you can see there automatic steering. We control, of course, the balance as well with robotic operating system. And we can do very simple chemistry experiments at the beginning. What's very nice is the framework, right? The infrastructure allows us to do all the task and motion planning, skills, all of that controlled by robotic operating system. Okay, so I'm going to actually skip all the way to where we are. I'm going to end here, actually. Do you guys remember Organa? Right? So now, what happened between where we did that in 2022 and 2023 is what? How many of you have used ChatGPT or Gemini? Raise your hand. Okay. How many of you have used it to write a paper? Okay. No, come on. Have you optimized a paragraph for your paper at least? Be honest. Did you optimize your abstract? Raise your hand. Okay, good. There's only one honest person here, right? Okay. Anyway, ChatGPT is actually a very useful tool, okay? Because it allows you to actually interact with a human, but it's not enough. You need to plan. You need to verify it. You need to make sure it's not saying bullshit. You need to actually control it. So we built a huge system around it, okay? A computer vision system and a planning system, and we built a robot that actually can do electrochemistry. It's called Organa. It's not perfect. You can expand it more and more, but I want to show you, I'm going to end basically with a video of graduate student Marta Screta talking to the robot and doing some chemistry. So here are all the different modules in Organa. As I told you, robot execution modules, experimental planner, perception, etc. So it's not just connecting ChatGPT to a robot. It's a lot of stuff, but it's all open source, and you can do it too. So I don't have the control of the video. So I'm going to speak as I'm showing you this. The robot is going to be asking Marta all of the different questions. It just doesn't know enough about the experiment. So it's asking Marta, can you tell me what am I doing, etc. Do you guys remember Purvey diagrams? So basically, it's trying to do Purvey diagram for quinons, okay? And I'm sorry because it takes too long, but amigo back in the back, can you fast forward a little bit the video? To about here. Here. Put the mouse here. There you go. There, yeah, thank you. Computer vision. So it needs to know what is what, okay? Now you need to compile it and then run it in parallel. Because if the arm is moving and you can run a pump, you can do both at the same time. So that's the basically electrochemistry experiment being done by Organa. Like all ChatGPT-based systems, it also writes a report about the experiment. Okay, and I'm gonna skip that. So we need to build all these modules, and what is really cool about this is that, for example, it has an electrode polisher. The electrode polisher by itself, we publish a paper, a preprint on, for example, what is the best technique for polishing electrodes? How many of you think it's a figure 8? You guys remember that? Figure 8 electrode polishing, you remember? It's not true. The robot can do it any direction and it doesn't matter. So it's really not true. So anyway, that's basically the story. So we built this robot that can do all sorts of different things. And I invite you to actually help us build it. Now, if you ask the question, what is faster? The human can still meet the experiment faster than the robot. These robots are very slow. Okay? But the human is way happier. This is the NASA task load index. Humans are less frustrated. They don't have less mental demand, etc. So the robots will help the scientists do better science. Okay, and with that, I'm just gonna end my talk. I'm not gonna even show a picture of my research group at the moment because I cannot switch slides. So I want to end my talk. Thank you for the time and sorry for going over about 8 minutes. Thank you very much.
I mean, I believe there are several questions now. You can extend a little bit more. No, there's no way.
Yeah, questions. Yeah, I just felt guilty because I went over time. Yeah, okay, back there, the honest guy. Yeah. Mr. ChatGPT.
Even more honest. Do you foresee violent reactions of researchers when Organa will start to command tasks inside of received tasks?
This is a question I always get. And this is my answer. My answer is a poem by Jorge Luis Borges about chess. So Jorge Luis Borges wrote a poem about chess saying, who is the god behind the god that moves the player, that moves this piece, that starts this game of dust and agonies? So it's talking about who has the action here, who has the will, right? In this case, we built the robot. Like basically, Antonio is going to build his robot. He's going to tell the robot what to do. You're going to make solar cells. So the god behind the god is Antonio, right? He's the one who's going to define what the experiment is all about. The robot is a catalyzer, right? So now I made a very bad joke about grad students. I shouldn't have made it, because the same way PowerPoint enabled us to give these presentations, or my thing, beautiful AI, but we use a tool to actually give presentations, or this microphone. We scientists are more efficient by all these different technologies, like YouTube. We're showing the talk in YouTube, right? So self-driving labs are going to help us do that. If we can make organic lasers, in this case, 100 times faster than traditional, that's how actually we can make materials 100 times faster than people really can do it. Then we can actually discover 100 times faster, hopefully, and find technologies for humanity better. So I think as humans learn how to build self-driving labs, I imagine grad students building these little things that allow them to do the experiments faster. So I don't think they're going to lose their jobs. I don't think the robot is going to be our overlord. But everybody asked me that question because obviously it sounds scary, right, when a robot starts doing science. But I think that's what's going to happen, at least in the near future. You can always read many science fiction stories and then, extrapolate. But at the moment, this is where we're going to be in the next decades, probably.
Thank you.
Nikita.
So ChatGPT notoriously gives you sometimes bullshit answers.
Yes.
How do you control for that in a self-driving lab?
So I skipped the slide. We have a system called Clarify. Clarify takes the output of ChatGPT and does what many people do nowadays, chain of thought, goes back to the model to refine until the model is able to find the right answer. Otherwise, it tells the model was not able to give me a valid output. But now we're working in a very large collaboration on safety. How to make these robots safe. You have to build a bunch of systems of how to make this safe, and we start thinking about it. So stay tuned for a preprint from us coming out very soon about the safety of self-driving labs, which is a very interesting topic. Yeah, so we are working hard. That's why I told you there's a huge system around ChatGPT. I started a company called Axiomatic AI with Dirk Engler at MIT, that the only thing it's doing is building photonic circuits with AI, right? Literally building integrated photonic circuits. And for that, there's so much formal validation after ChatGPT suggests something, that basically that is the system that you build, not necessarily the ChatGPT module is just a little piece of what you actually code.
Yeah, also I have a curiosity, Alan.
Yes.
So the way you show at the end is very anthropomorphic.
Yes.
Would we really need to go in an anthropomorphic way, or there is a different way to do it? I mean, which is still robotized, but not an anthropomorphic way?
Well, in my lab, we do both approaches. So we build these little small reactors, 3D printed reactors, and pumps, as you saw, and so on. And then we have this futuristic view that anthropomorphic robots are going to be important, because I believe that a lot of the procedures that are done in organic chemistry, material science, etc., were designed for humans, even pressing the buttons in the equipment and so on, right? For example, if you want to do chemistry in a hood, you have the hood there. So we're working on how to put robotic arms inside of the hood, right? So you can actually do chemistry with things that are evolving gases, or even more interesting, chemistry inside of a glove box. So a lot of the things that we built are all made for hands. For the moment, I think if we automate these hands so easy for use for an organic chemist or an experimentally inorganic chemist, then the same procedures can be translated with a $4,000, $10,000 arm. Later, we can always build these high throughput machines as well. But I believe the democratized future of a robot that can see, can talk to you, can carry out experiments will liberate us from a lot of different things. For example, powder dispensing. How many of you spend a lot of time powder dispensing in a lab? Raise your hand if you have spent a lot of time powder dispensing. Like, do you like powder dispensing? If we were able to actually automate powder dispensing, for example, it will make us so much more powerful.
Which is not simple. Huh?
It's actually not simple.
It's not simple.
You need computer vision. You need a lot of things for doing good powder dispensing. Yeah.
Okay, please, Alessandro.
Thank you. Very interesting. And okay, I'm not sure if I fully understood everything. I have a series of questions. I will compress everything.
Please.
I see in some graph you put some of the results of your combinations coming from the procedure you outlined, comparing with existing data, previously obtained data. What is the path across those points that you determine. So could you could your approach define a process to optimize your performance and go from one random selection of parameters or a network selection of parameters and then to progressively improve the things?
That's what we do, exactly. That's Bayesian optimization. That's what we did.
And
the plot I was not finding was going to show something like that. When you keep going.
So then I have another couple of things related to this.
Go ahead.
And what happens if you're foreseeing detect some molecules which doesn't exist and maybe cannot be properly synthesized with current methods? So is there any tool to imagine new approaches to develop new kind of molecules which would be optimal for your application, but still there aren't? And last question related to the previous question from Aldo. So if you have, I'm a chemist in my formation, I spend time mixing and so on, and it would be very nice to work instead of milliliters or even larger quantities to work with very small quantities. And I guess that your approach might be working with microfluidic approaches. Mm-hmm. I'm not expert of this, but did you ever explore this? And do you have a corresponding behavior between properties obtained in bulk quantities and some microfluidic approach, or with very small quantities, let's say?
So let's talk about them. Let's talk about them in order. The first question I was starting to answer, but I'm going to continue answering. I'll give you one example that is very good about optimizing that way. I have a paper with Christoph Brabeck from Erlangen on organic solar cells for tetra-component organic solar cells. Usually they are only explored 3 components. This was the first paper on 4 components. So we did a baseline. We ran about 1,000 experiments to build an entire pyramid, like the pyramid you have here in Rome, but like a pyramid of data points that basically is all the phase diagram of this quaternary compound mixture. That was 1,000 experiments. Then, with those 1,000 data points, we can simulate or see how an optimization would look like. And the average is 35 experiments. So with an optimizer, you can do 35 experiments. And we did it also in the experiment too. But we also, because we have the entire data set, we can see how long it would have taken. So it's dramatic. The optimizer took only 35 experiments over 1,000 that you would have taken if you had run all the experiments at once. So that answers the question about the optimizer. Now the question of going beyond what the robot can make, right? Obviously, generative models, quantum chemistry, all sorts of tools could tell you, this is a molecule that my robot can't make, but I still want to test it. So Martin Seyfried, which is now a professor in North Carolina, one of my former postdocs, and I wrote a paper called Route Score. Route Score, you think about scoring a synthesis scheme as if it was the subway, okay? Like in Rome, you guys have all sorts of transportation things, like motorcycles and all sorts of things here in the road. It's a very dangerous place, right? But anyway, you take the subway first, and then maybe you take a scooter, right? So you plan it like this, like if you were transporting yourself in Rome. So the robot will be the subway, and the scooter is a one-step synthesis. So we actually now can measure the efficiency of a synthesis by how many steps can I make in the robot, and then how many steps I can do before or after by hand. So with that measure, we can actually try to be as close as possible as what the robot can make, and maybe post-process or pre-process. So you can read our paper called Route Score. So that gives you an idea of what we're thinking. There's all the things we're thinking. And finally, your question, microliters, etc. Yes. So as you saw, one of the things I'm thinking is a robot doing this. But obviously, we collaborate with a lot of people. And I collaborate with Eugenia Kumacheva in Toronto as well. She's a microfluidics person. So we have done nanoparticles with microfluidics. We also have done, like that research even more. We have a paper, hopefully about to be published, on organoids. We have microfluidics with organoids, and we're dosing cancer medicines in order. And you use an optimizer to figure out what is the best multi-stage combination to kill this cancer, right? And we're using microfluidics. I would say anything goes. Really what we're saying is you automate any experiment with data science and close the loop. So it can be microfluidics, macrofluidics, batch synthesis, flow synthesis. I'm really agnostic about how you do the experiment. It's your favorite way of doing it. I think it's the incorporation of AI and data science into it that makes it a little bit more powerful, because Now you can automate it and then, do other things. Yeah. Yeah. Okay. Honest man again. Yeah.
A more technical question now.
Yes.
Up to now, have you considered among your parameters also green parameters such as energy consumption or use of greener solvents or similar environmental indicators?
You make me very happy with the question because, yes, we have one paper with Merck USA where we optimized a catalysis for process chemistry. At least we're trying to minimize the amount of palladium and things like that, trying to make it greener a little bit. But we are thinking in the Acceleration Consortium in Toronto a lot about that idea. How can we make the self-driving labs green? And we actually were forced to slow down by the Canadian government told us to get this grant, you need to work with indigenous communities, people that think about indigenous science. So after learning about indigenous people, they say, you have to think about 7 generations before you and 7 generations ahead of you. Right? There's a philosophy that is very different than our, let's publish a Nature paper kind of philosophy, right? Mm-hmm. So it's more about thinking about the problem. So we're now saying it's like Enzo Ferrari. You accelerate and then slow down in the curves and then accelerate again and then slow down. So that slowing down is the important piece of thinking about, am I green? Am I sustainable? Am I not going to be worse than what I started? So we're about to publish a few papers on that topic as well, trying to write a manifesto. And our collaborator, Morphy, they think that maybe we even have to go to the conventions. Like, how there's a chemical weapons convention, having like a self-driving labs convention that defines how these self-driving labs are going to operate in terms of the environment, humanity, safety, etc. So there's a big component of our big grant thinking about this, because obviously we cannot be irresponsible. It's a little bit like Oppenheimer and the atomic bomb. It could be not so good to make molecules very fast.
Okay, so I don't see other questions. Let's thanks Alán again. Okay, so now it's time for the pergamena or something like that. I mean, for the prize. Okay, so I go and take it. And okay, use this one. Okay, so Nikita. So, yes. I invite also the representative for the other side of ISM, Daniele and Antonio. Please come here. So then, I mean, these are my co-directors. Okay, in the other side. So the first one, please come here. Okay, please. Okay. Okay. So Nikita. So so you were inspiring all of us with your research activity, and then it's really a pleasure for us, for all of us, I mean, for the Institute, to award you of PRISM 2024. Alán, so it was really an incredible pleasure for us. I mean, your work, because it's really inspiring now, the activity we are doing. And as you have seen, Antonio is your follower. So it's really a pleasure for all of us, for the Institute, for all of us that are working in science, to award you PRISM 2024. Thank you. Thanks a lot. Thanks, Alán. Great. So, so it's really, we really thanks our winners. I mean, and this will. So they are inspiring. They will inspire all of us and many in the world, as we have seen. So for today is almost all. I thanks all the work you have done. I mean, in supporting all the jury, making nominations, and asking nomination around the world. So it's really helpful, because you have seen, I mean, how beautiful is science and to innovate in science. So now we have a toast, okay? All together, we need to go somewhere, I believe downstairs. Gianni, downstairs? Yeah, downstairs, so we need to go downstairs. And so let's thanks again, and thank you.